just remembered I forgot to open the PowerPoint, so it's going to take just a minute on that one. Oh, Nigel, for being late, I have a gift for you. Yes. How did you know? All right. You're also in different equation, right? It's not quite ready. I doubt if I have time at lunch today to get it done. I only have 45 minutes for lunch, and I think it's going to take a little more than that. So, okay. I think we're ready to go now. First thing I want to know, any questions or anything we've done so far? Any questions? Okay. All right. According to my mark, we're on page 43, section 2.1, chapter 2. Chapter 2 is matrices. 2.1, operations with matrices. And example 4 is finding the product to two matrices. We've talked about it, but we haven't actually done it. So let's do our first one. Find the product of A and B. Well, let me get my pen. Well, the pen won't come up. There we go. Okay. Now, where matrix A is -1, 3, 4, -2, 5, 0. Okay. Matrix B is -3, 2. This is so aggravating. -3, 2, and -4, 1. All right. And we're asked to find the product AB. Okay. Now, I know it's a lot of writing, but I would write down the two matrices again. I wouldn't try to do them in my head, especially not to begin with, and maybe not ever, okay? It just, I think it's safer to write them down. Okay, question first. Would you be able to add these two matrices? No, because why? They're not the same size, okay? Would you be able to subtract those two matrices? No, they're not the same size. Can you multiply those two matrices? We hope so, because they told us to, right? Here's what I suggest first, and you don't have to. It may be too simple-minded, but to me it's a good procedure to do. What is the size of this first matrix? 3 by 2. What's the size of the second matrix? 2 by 2. Okay? Now, based on that, can we multiply these two matrices? What's required? The inner numbers have to be the same. So what I suggest is basically, since they're the same, wipe them out. Okay? Now, what's left? A 3 by 2. That's going to be the size of the product matrix. A 3 by 2. Now, I go so far as doing this. You don't have to, but I found it useful. Since it's a 3 by 2 matrix, I'm going to put blanks in here. 3 by 2 blanks, right? Okay? Now, this is just the way I do it. You don't have to do it this way if you see a better and easier and more obvious way to do it. Name the position of this blank right here. What would you call that entry if you knew it? Let's call it C. C what? What subscript? Say again? 1, 1. Okay. That is the key for how you multiply the matrix. Okay? Okay? You take the first row of A and the first column of B. Okay? So multiply those entries together. What does this give you? 3 is, you're adding now. Okay, 3 minus 12, -9. You got it. First entry. of a multiplied matrix that you've ever done, right? You got it. Which entry do you want to do next? Go right, go down, where? You can go anywhere you want to. I'm not telling you where you have to go. To the right. Okay, what is the name of that entry? The same? 212? Oh, 1, 2. Got it. I can't hear well. Okay. That's the 1, 2 matrix. So what do we do? First row of this one by the second column of this one. That would be -2, which is a little louder. 1. Excellent. Okay. 1. Okay. Name that 2. Name this space here. What's that one? A little louder. The 2. 2, 1. Okay. First column. 2, 1. So where do we go here? Second row. First column. Very good. What does that give us? -12 plus 8 is what? -4. Is that what you said? Okay, I can't hear well. -4. All right. Next. Name that one. You want to name it before? 2, 2. So where do we go? Second row. Second column. That gives us 8 minus 2. 6. Okay, very good. 6. Okay. Next. 3, 1. So where do we go? Third row. First column. What does that give you? Say again? -15. Say again? Still -15. You got it, because that was a 0. -15. Next or last? Okay, 3, 2. Is that what you said? Okay. So where do we go? Third row, second column. That gives you 10. So that gives you 10. You just multiplied your first pair of matrices. Okay? Do you see how that works? Okay, let's see. Did they get it right in the book? Look at that. Good for them. They did very nicely. Do you see how it works? Okay? Now, I'm not always going to be running my fingers for you, so get used to it. The key is take it slow. Make sure you're doing the right rows and columns. You do this process all along. The package we used before we used Screencast-O-Matic was a package called Tegrity. A little bit easier to use and simpler in many ways, but it was more expensive and the school didn't want to pay the money for it, so they went for the deluxe model. Okay, so, but I had heard about it, and thought, who needs something else to do, But then I was asked, we had a Math 110 class. We ran a day section and the evening section, and we, I believe it was that class, I think it was. And it turned out that, may not have been, some class. We were running a day, and it may have been business math. I think that's what it was, business math. And we were running that. One section had 6 or 7 students in it. The other one had 4 or 5 students in it, something like that. Anyway, they were going to cancel both classes. And I said, can we combine them and make them one? They said, sure. If we can get 10 students, we can do it. And so I met with both classes, and I was, most of them could take the day class, but not all, and hardly any in the evening class was a smaller one already, and hardly any one of the day students could move to evening. So I wasn't going to have 10 unless I did a remote thing, okay? So I said, okay, I'll try this integrity thing. So I tried it, taught my first class with that. And one of the things that, as I was learning it and teaching it, I saw how powerful it was. I really didn't have to change the way I taught. It's just, getting used to it. And we were on they had training online or conference call or something like that. It was a conference call because we could talk with people. So I was on a conference call with them, and they were asking, what improvements would you like to make? I said, can we have 2 pens? Because I can do this all day long here, but I needed a pen to do it for the people who can't see me, my arm waving. They said, no, we hadn't thought of that. No one's asked for that before. I don't know any way we could do that. I would love to have the 2 pens. That way people who aren't here, they can see what we're doing. But hopefully I'm talking loud enough and obnoxiously enough that, it'll get the point. All right, before we turn the page, there is a blurb here on Arthur Cayley. He was credited with giving an abstract definition of a matrix. He was a lawyer by profession, but we won't hold that against him. And he did a lot of work on the early things with matrices. So this cannot be a source for your paper, but this can give you an idea of where to go if you are interested in doing them. They mentioned 2 other mathematicians here, 2 Americans, Benjamin Peirce and his son Charles Peirce. And it says that the 3 of them developed what we call matrix algebra. So there's 2 more names if you wanted to write on either of those, or development of matrix algebra, how did they do it? There's several paper topics you could get right there. To the point of quarter of the class is already turned in the papers, okay? Which means 1 student. So the others of you, let's get moving too. Let's not put it off too late. All right. Now, there's a little discovery here, and usually these press the limits a little bit and may introduce us to something that's, we say, what? But may not. I think this is pretty simple. Here is matrix A. Is 1, 2, 3, 4. Very creative matrix there. And here's matrix B. 0, 1, 1, 2. Okay. It says calculate the sum of those 2. So we can do that without writing them down, can't we? What size was that? Or can you add those? Let me ask that. Why? Same size, okay? And what would be the result of that addition? 1, 3, 4, 6. Okay, very good. We're really sharp this morning, aren't we? Okay, how about B plus A? Can you do that? What does that give? Say again? One, 3, 4, 6. Absolutely. And guess what? Those are the same. So what we've just illustrated, may not have demonstrated it, but illustrated, can't say for sure, but it appears that addition of matrices is commutative. It doesn't matter which order you do. Why? Because you're just adding the corresponding elements, and addition of the elements you know is commutative. So yeah, it's got to be. Okay? And Marcus is here. Just missing Jonathan. Okay. Now, let's do a similar thing, and let's do the product. AB. Can you do that? 1, 2, 3, 4 times 0, 1, 1, 2. Can you multiply those 2 matrices? Yay or no? Yes, you can. What size is this one? 2 by 2. What size is this one? 2 by 2. What makes you able to multiply them? The number of columns of this is equal to the number of rows of that. So your result is going to be what size? 2 by 2. All right, you're stuck, aren't you? Okay, just repeating the same thing over and over. Okay, let's do the multiplication. Oh, You like my blanks? Okay. It's a 2 by 2, so I know I've got to have those 4 blanks filled in. Okay? You pick one, I don't care. Pick one. Name it. Okay. 1, 1. We're going to do 1, 1. Let's call it this is B1, 1, 2. Okay. 1, 1. Okay? What will you multiply there? First row of A times the first column of B. Oh, that's a 0. Okay, what do you get? No, that's a 0. Huh? 0? That's a 2. 2. Okay? You get a 2. All right? Agreed? Find the position that you're looking for. What's the name of this position? Oh, perfect attendance. Way to go, team. All right. Oh, and for having perfect attendance today, y'all win a prize, okay? We had one prize earlier for the first one here. We had another one for showing up. Now, these for having perfect attendance, y'all get a prize too, okay? Full of prizes today, okay? Or full of something. Never mind, okay. Now, we were talking about how to multiply matrices. And since a couple of you came in after we talked about it, how I suggest, and this is how you, okay, first, you look at the sizes of the 2 matrices being multiplied. The number of columns of the first matrix must equal the number of rows of the second matrix, or you can't multiply, okay? So this is sort of a very simple one, and they're the same sizes, so everything's the same. They're both squares, so no problem there. But you don't. That's not required. What's required is the number of columns here equal the number of rows there. And what I suggest, just cancel out those 2 numbers. They've got to be the same, and your resulting matrix is going to be the number of rows here by the number of columns there. So it's a 2 by 2 as well. You're not always going to be that case, but it will always be the case. These 2 ones have to be the same. The resulting is the outside. So, we did the first one. What's the name of this position here? The what? 1, 2. First row, second column. So how do we do the multiplication? First row of the first one times the second column of this one. So that would be 1 plus 4, 5. That will give you 5. Okay. Next. Name of position. 2, 1. That would be right here. So what would we multiply? Second row by first column. That is a 0, by the way. 0, 4. Okay. So that will give you a 4. And the last position, what's that name? 2, 2. So what would you multiply? Second row by second column. So that would be, that's a 3, huh? 3 plus 8 is 11. Say again? 11, right?
Can you go back one more time?
Okay. All right. What you do, okay, first, make sure you can multiply. Put the size of this and size of that one. If these 2 numbers, the other 2 numbers are not the same, you can't multiply. If they are the same, you can. So once they're the same, wipe them out. This is the size of the resultant matrix. The number of columns here, rows here by the number of columns there. So this happens to be a 2 by 2 as well. This is a very simple example, so don't expect all of them to be this way. Okay. So then what I do, and this is just the way I do it, I put a blank, 2 by 2 blanks there. Okay? Then name the position. Like this one is position 1, 1. First row, first column, right? So how I multiply is first row of the first one times the first column of the second one. So that would be, no, that's a 0.
Oh, 0.
0.
2 times 1. 2.
Yes, it's 2. 0 plus 2 is 2. See?
So you add them.
Yeah, you multiply and add. Yeah,
Okay.
multiply and add, multiply and add. Yeah. Okay? It's sort of like distributing. Okay. Got it?
Mm-hmm.
All right. Now, what we're testing here, they say now, let's do BA. Okay? We won't say what that is, but BA. And what would that be? Matrix B, which is 0, 1, 1, 2, multiplied by matrix A, which is 1, 2, 3, 4. I can remember that one. Can we multiply this way? How do you check? Determine the sizes. What's the size of the first one? 2 by 2. What's the size of the second one? 2 by 2. Are the inner two the same? Yes, they are. Wipe them out. And then you're left with a 2 by 2. So the result is going to be, the product matrix is going to be a 2 by 2. I like to go on and fill in the gaps, blanks there. Put the blanks there so I know which one I'm looking for. You choose. You don't have to choose the upper left. You can choose any one you want. Name a blank. Second? 2, 2. Oh boy, he's getting creative at this point. Okay, 2, 2 would be down here. What do you multiply to fill in that? Row 2 by column 2. So row 2 here by column, row 2 here by column 2 there. Okay, what would that give you? 2 is 10. Oh my goodness. Okay. Next, give me another one. 2, 1. Which one's that? Second row, first column. So we do second row, first column. That would be is 7. 1 plus 6 is 7. See how hard the math is in here? Second row, first column. That's why I don't like to do them this way. I forget which one I was doing. Pick another one. 1, 1. All right. Okay. And what would you do to get the 1, 1? First row by first column. What would that be? 0 plus 3 is 3. Okay. See, here's the thing about matrix stuff. The math isn't hard. It's the procedure. It's the repetitiveness. It's the tediousness of it and the opportunity to make lots of little errors, which one little error will throw you way up. 1 remaining. What's that? And how do we get it? Except? Guess again. What position is that? First row, second column. Okay. So what would we do up here? First row, second column. That gives you 4. Okay. Now my question to you now is multiplication of matrices commutative? Absolutely not. Look at this one. These two are definitely not equal. They're not even close. Were you going to say something?
I'm still lost on how you multiply.
Okay.
I don't know.
Okay. See, y'all threw them up, but picking random there. Okay. You pick a position for me. Down here. Any one of those 4 positions. Pick one.
It should start like
1,
1, 1.
1. Start with 1, 1. What you do to get the 1, 1 position here is take the first row of the first matrix by the first column of the second matrix. You multiply the entries and add the products together. So this would be
0, right?
0
And 3.
plus 3. That gives you your 3.
Okay. Now, I think
Okay.
this is the direction he was going in.
Yeah. Yeah, I know. Whose fault was that, huh? Okay. It's okay. All right. Make sense? So guess what we've concluded? Guess what? Up here, we can't positively conclude that addition is commutative unless you think about it, and the addition of each element is commutative, so therefore the addition of matrices is. But guess what? All you need is one example that the multiplication is not commutative, and you can say, no, it's generally not commutative. But let me give you a little caveat here, too. Y'all like caveat? No, I don't like it. It's too salty. Never. Okay. There are some matrices that the commutation is equal. And guess what? They are really special matrices. Most matrices, no. In fact, if these were not square matrices, okay, but rectangular ones, there's a good chance you can't even multiply them in the reverse order. Say if this was a 3 by 2, and that was a 2 by 2, like the first example was, you can do this and your result would be a 3 by 2, right? But then could you multiply a 2 by 2 by a 3 by 2? No, because the middle two numbers, this would be a 2 and that would be a 3. You can't even multiply them. So definitely, matrix multiplication is not, I don't want to say never, but not in general commutative. There are a few matrices that when you multiply them, they in reverse order, they give you the same answer. When you find one of those, cherish it. It's a very special matrix. Okay. So, let's go to example 5. Any questions so far? The more you do these, the better they get. Right? Okay. You buy that, I've got, okay, never mind. Let's see if we can multiply these two matrices. Okay? The first one's a 1, 0, 3. I usually do rows across. Last term I had a kid in the class, and he always liked to do down. I guess he was from Sumerian background or something, you know, and it just, I mean, he would call out something, and I'd say, that's not right. Oh, no, I was doing the other way. Okay. Or he was faking me out one. Never mind. No, 2, -1, -2. Okay. And then we have a -2, 4, 2. And we have a 1, 0, 0. I can't stand to do rows like that. They're so terrible. And -1, 1, -1. Okay. Now, they wrote them next to each other, meaning they suggest you need to multiply them. I'm not even sure you can. Can you? What's the size of the first one? 2 by 3. What's the size of the next one? 3 by 3. Yes, you can, because the 3's are the same, the innermost. And what's your product going to be? 2 by 3. Okay, so then I'm going to go on and put my blanks in there. I know I need 2 rows of 3 columns, right? Let's be a little more organized this time and start with the upper left, okay? You don't have to, but just because we're just learning it. Once you get the hang of it, you can do it any way you want to. Okay, let's do that first one. What is the name of that first blank? The 1, 1 blank. So what do you multiply? The first row of the first one by the first column of the second. Okay, so here we go. Which adds to? Second? -5? Fantastic. Okay, you want to go across? Okay, what's the name of this one? 1, 2, buckle my shoe. So what do we do? First row, second column, 1, 2. So this will be 4, which is 7. Very good. Do you see what we're doing? Okay. What's the next one? 1, 3. So what do we use? First row, third column. That's going to be 2, which is -1. Very good. Does everybody see it? Got it? Okay. Name the next one. It's a what? 2, 1. So what do we multiply? Second row by first column. And that gives us? Really? -4. That would be a -5, right? Which is a? Second?
No. 3, -3.
-3. All right. Okay. -3. Okay. Next blank. What's the name? 2, is that what I heard? Okay, so what do we multiply? Second row by second column. And that will be 8. And what would that give you? 6. Very good. Okay. What's that last blank's name? 2, 3. So what do we multiply? Second row by third column. And what does that give us?
0, 2.
Which is? 6. Very good. You see how it works. For some reason, my pen didn't write. It's still not writing. Oh, there, it sort of wrote. Okay. All right. Let's see. How did the book do? -5, 7, -1, -3, 6, 6 with a pale 6 at the end. Okay. Got it. Okay. Can we do B underneath it? I think we can. Let's try B. 3, 4. -2, 5. I can't write. Going to try to multiply that by 1, 0, 0, 1. Okay. I'll try to clean that up just a tad. Probably will clean it up too much, but let me see if look at that. Okay. Where do we start? Okay, the size. What's the size of the first one? 2 by 2. What's the size of the second one? 2 by 2. Can you multiply those two? Say again? Yes, because the middle numbers are the same. What's going to be the size of your product? 2 by 2. Okay, so I can go on and fill in my put my blanks in. Okay, and you pick a blank as long as it's the right one. The 1, 1. So what do we multiply? First row of this one by first column there. That gives us a 3. Gives us 3. Okay, y'all are quick today. Okay. Next. 1, 2. So we would multiply first row by second column. That would give us a 0, 4. What does that add to? 4. Okay. Pick another one. Say again. 2, 1. Okay, what we multiply? Second row by first column, and that would give us a -2, which is -2, right? Okay. Uh-oh. Does this belong to someone in here? It's a plug in the wall. Looks like for an iPhone or something. It must be from my trig class yesterday, because I don't think anyone was in this room last night. Okay, I'll wait to see if someone comes by. Otherwise, I'll probably put it in the office there. That looks pretty valuable. Okay. All right, what's the last one? 2, 2, so what will we multiply? Second row by second column, and that gives us a plus equal 5. Now, do you notice anything here? I know you've been digging around in the trees here. Have you looked at the forest? It's the same as the first. They gave you the same thing. Now, if this were regular math, if you multiply something by something and got the same thing that you had to begin with, you would call it the multiplicative identity element. Now, you think that matrix could be a multiplicative identity element? Yes, it is. In fact, guess what we call that matrix? The identity matrix, okay? What constitutes an identity matrix? 2 seconds. And we're way ahead. We haven't covered this in the book yet, but I'm going to go on and introduce it to you. Maybe 3 features. First feature, identity matrices are always, y'all don't know what that means, do you? Square. I painfully know what it means. I had an older brother and a younger brother. The older brother and I were 2 years apart. We were kind of like best friends. You know, we always did everything together. Short time I was bigger than him anyway, so we were almost like we were the same age, but we weren't. But then the younger brother was 3 years younger. He was a little bit of a rebel. I was a pretty good kid. Dan wanted nothing to do with being a good kid, okay? And because I usually obeyed the rules, he named me L. And to this day, quite often, he'll say, "Hey, L." Don't even remember what. You know where he got that? Let's see if you can do it. L7. So I was L7, I was a square, okay? It's not that funny. It was painful. Okay, no. You're laughing still. Okay, no. And to this day, he still calls me L. Okay, I still hit him up. No, I don't. Okay, so this is called the identity element. First thing it is, it has to be a square matrix. Second feature, the one, that's a diamond. Okay, I'm a diamond, really. Okay. Second feature, you got ones on the diagonal. The main diagonal are all ones, and everything else is zero. So those are the three features of an identity matrix: is square, main diagonal, all ones, zeros everywhere else. Okay? Now, how we refer to that is the I matrix, but because this is a 2 by 2, we call it the I2 matrix. Okay? You don't need to know that yet. I'm just giving you that since we hit it here. Let's move on to number C, or letter C. Okay. It means yes in Spanish. Okay. So we're going there. Okay? Now, C is 1, 2, 1, 1, negative 1, 2, 1, negative 1. Okay. First, can you multiply those two? Why? Okay, they are the same, 2 by 2 by 2 by 2. If that was a 2 by 3 and a 2 by 3, they're the same. Can you multiply those two? 2 by 3, 2 by 3, the middle numbers aren't the same. So just being the same doesn't qualify. But if they're the same in both square, yes, you can. Okay? So, you can. What size is going to be your product matrix? 2 by 2. So I'm going to go on and put my blanks in there. Let's start filling in the blanks. Where would you begin? 1, 1, okay. So what would you multiply to give you the 1, 1 entry here? First row here by first column there. What does that give you? Negative 1 plus 2 is 1. Okay. All right. Where do you want to go next? 1, 2. Okay. What would you use to get that? First row by second column. That gives you a 2. Gives you 0. Wow. Okay. That's not worth much, is it? Okay. Next. 2, 1. So what would you multiply? Second row by first column. That gives you negative 1 is. Y'all are in a rut, aren't you? Okay. And then, goodness gracious. Okay. This is outrageous. Okay. Finally, what's that last element? 2, 2. So what will we multiply? Second row by? And that gives you? One. Absolutely. Guess what we got as our result? The identity matrix. Okay? Now, if the identity matrix is acting like the number 1 in regular math, that when you multiply a matrix by 1, you get the same matrix, then if you multiply one number by another number and your answer is 1, that means these two must be numbers, inverses of each other, reciprocals of each other. Now, we don't have reciprocal matrices, but we do say this is an inverse matrix for that. Don't worry about it yet. We're not there, but just letting you know, anytime you multiply two matrices together and you get the identity matrix, then these two are okay. Let me take that back. Not every time you do that, but when you multiply two square matrices together and you get the identity matrix, then these two square matrices are always inverses of each other, even though we haven't identified what that is yet. Okay? And these are those special matrices I was talking about earlier. All right, leave that alone. We'll come back to that later. Let's do D. Okay? Ooh, D is weird, isn't it? D is a 1, -2, -3. Give me a name for that kind of a matrix. Has two names I could call it. Say again? It's a row matrix. Also, you could call it a Thank you. You awake yet? Okay. I wasn't sure. Okay. Thank you. All right. It also could be called a column. A row vector. If it has a single row or a single column, it can be called a vector. So that can be called a row matrix or a row vector. And how about that second one? Column matrix or a column vector. Exactly. Okay? Now, here's the dumb question. Can you multiply those two? Why? 1 by 3. This is a 3 by 1. And guess what? I don't need the column getting carried away here. Okay? And guess what? These two are the same. And what size are you going to wind up with? It will be a matrix, but it only has one element. So how do we get that 1 by 1? First row to first column, which is only row and only column. What does that give you? 2. A little louder. 2 plus 2 is 4. Didn't know we'd do this high level math today, did you? Okay. And which is 1. All right. There we have it. Wow, all that for 1. Okay. Good deal. How about this? Let's take those same two matrices, and I'm going to erase a little bit here. And we will do 2, -1, 1, and see if we can multiply that by 1, -2, 3. -3. The question is, can we? Why? This is a what? 3 by 1. What's this one? 1 by 3. Yes, you can, because the ones are the same. But what size are you going to wind up with? 3 by 3. Did you ever thunk it? Doing one way, you get a single 1 by 1. Now you get a 3 by 3. Same two matrices, but reversing the order. So let's pick one. What you want to start with? Which element? Name one. The 1, 1. So how do we do that? First row by the first column. What's that? 2. That's all that you wrote, folks. 2. Pick another one. 2, 1. Okay, where is 2, 1? right here. Okay, so it's okay. So what do we do now? Second row by first column, that gives you second -1, okay? And remember where you said that goes here, okay? Pick another one. Second? I couldn't hear. 1, 3. Let's do 1, 3. Where is 1, 3? Upper right, right? First row, third column. So what do we multiply? First row by the third column, and that would give you -6. Remember where you're doing. That's why I sort of like to do it in order, because I forget what I'm talking about, okay? Pick another one. This is like Jeopardy or something, huh? Second? 1, 2. Okay, where is that one? Building in the top row for tic-tac-toe. Okay, okay. So how do we get into that one? Okay, first row by second column.
Yeah.
You do that? -4. Right? -4. Pick another entry. 2, 2. Okay, how do we do that? 2, 2 will be right in the middle there. Second row. Yep, and that multiplies to be 2. Next, you just tell me what to fill in. Where? Oh, 2, 1? 3, 1. Okay, what do I do? What's that answer going to be? 1. Good. Pick another one. 3, 2. Okay, what would that be? -2. That goes down here, right? 3, 2. Okay. Next. 2, 3. What would that be? Second? 3. Okay. And what's the last one? And what would that be? -3. Does everybody see that? We got it going fast at the end, but I thought I don't need to always do my hands up there. Y'all need to see them. Let's see if they got them right in the book. 2, -4, -6. Good. 1, -1, 2, 3. And 1, -2, -3. Yes, yes. We got it right. Or they did too. Okay? All right. So, guess what? We did these two matrices, and we commuted those, and you happen to be able to do that. It did give you, are those two equal? Nowhere close. They're not even the same size. How could they be equal? So obviously the commutation of two matrices, when you can do it, the odds are you're not going to get the same result. You may not even get the same size of a result. But even if you do get the same size, you probably won't get the same result. Unless you happen to have one of those like that. Let's go on and do that one. Let's do this one. -1, 2. The book is asking you, I'm asking you to. 1, -1. And multiply that by 1, 2, 1, 1. We're going to do that one. Can you do it? What size? 2 by 2. Pick an entry. 1, 1. So what would you multiply here? First row by first column, and what does that give you? -1, which gives you 1. This isn't in the book. No extra charge though, okay? Pick another entry. Second, 1, 2. So what would you multiply? Column, that would be 0. Okay. Next. 2, 1. So you multiply. No. 2, 1. Second row by first column. That gives you 0. Okay. And guess what? Last entry, 2, 2. Second row, second column, 2, which is 1. Look at that. We wound up with that identity matrix again. So in this case, you commute these two and you get the same result. And like I said, those are special matrices. These are inverse matrices of each other. Okay? And they always give you the identity matrix if you have the inverse. All right. Good deal.
So inverse will always be
Commutative, yes, absolutely. Now, I also want to say this. Not all commutative matrices may be inverses, but there'll be multiples of an inverse. Say, if you multiply one of these matrices by 2, but left the other one alone, and you did that, I think you get a 2, 0, 0, 2. I think. I haven't worked through it. So that wouldn't be an identity matrix, but it'd be the multiple of an identity matrix. So play with that if you want to see. All right. Okay. We've played around with different operations of matrices. Adding, subtracting, and now multiplying. Guess what? We're going back to systems of equations. I wonder why we're doing that. Okay. Let's see. One practical application of matrix multiplication is representing a system of linear equations. Guess what? We've done that before, haven't we? And here would be the typical. Do you all have books now? No, you still don't. You have a book yet? Okay. So let me write it down. Here is a system of linear equations. A11 x1 plus A12 x2 plus A13 x3 is equal to B1. Okay? A21 x1 plus A22 x2 plus A23 x3. That's an ugly 3, isn't it? Goodness gracious. Is equal to, guess what that would be? B2. Okay? What would be the next row? A31 x1 plus A32 x2 plus A33 x3 is equal to B3. Okay. If you had a B4, you would need it after. No. Okay, now, the A's are just coefficients. We just put the subscripts on there so we can identify where they belong. The B's are just constants too. Okay? We just put subscripts on those to let you know which equation they belong to. The X's, all the X1s are the same variables, X2 is the same variable, X3 is the same variable, but they're different variables from each other. Okay, so that's what we got. Now, write that as a matrix equation. Do you know what I mean by that? Let's start with the coefficient matrix. What would that be? Just the coefficients. A11, A12, A13, A21, A22, A23, A31, A32, A33. Now, write a column vector that represents your variables. What would they be? X1, X2, X3. And let's write a column vector that represents our constants. Guess what they would be? B1, B2, B3. Now, why did I write the variables in a column rather than a row? Was it arbitrary? Why not? Exactly. This is a 3 by 3. You couldn't multiply it by 1 by 3. You have to multiply it by 3 by 1. Now, what answer would you get? 3 by 3 by 3 by 1. A 3 by 1. So that couldn't be a row vector either, a row matrix. It has to be a column as well. But does that give you the same thing? Matrix multiplication, A11x1 plus A12x2 plus A13x3 is equal to 1. That's exactly what we've got here. And A21x1 plus A22x2 plus A23x3 is equal to second row, first column. Second row, only column, B2. Sure enough, that's your second equation, right? And then the third is A31x1 plus A32x2 plus A33x3. Third row by first column is the 3-1 entry, is equal to B3. Yes, this is an exact representation of this in matrix form. Okay, you got your coefficients in a matrix, you got your variables in a matrix, and you got your constants in a matrix. Okay? Now, so what? Frankly, and by the way, you could name this matrix A times vector X, and that is a matrix as well, but I'm going to name it a vector, and this is equal to vector B. I indicate vectors by the book does it by bold. I do it by putting arrow. I don't write bold easily. It gets messy if I try. Okay? So sure enough, that's a lot more concise than this. Now, they're just going to leave it hanging there. Okay? Not very fair. Okay? They just leave it hanging there. We're going to come back to this concept in short order. Maybe not today, but soon. Probably Tuesday. Okay? Wait, Monday. Okay. I can't keep straight what day it is. Now they're asking you to go in reverse, and let's do example 6, which says solve the matrix equation AX is equal to 0. Now that's not the number 0, that's the matrix 0. Okay? Where A is this matrix, 1, negative 2, 1, and 2, 3, negative 2. All right. X is this vector. Maybe I should have done on a new page. X1, X2, X3. And would anyone want to hazard a guess what the 0 vector would be? 0, 0, 0. Okay. Now again, the 0 vector can almost be any size. Actually, a 0 matrix could be any size too. Every element has to be 0. But because your X has 3 elements, you have to put 3 elements. So sometimes we might call that the 0 vector with a 3 and a subscript, or subscript, to indicate it's got 3 0 elements. Okay? So basically what it's saying is write, yes. Oh, you're right, 2 zeros, you're right. Okay, sorry about that. I got carried away. Someone carry me away, please. Okay, 2 zeros, yeah. Because you're right, it's not a square matrix, it's that. And you only have 2 equations, so you can only have 2. So that's the 0 vector with only 2 elements in it. And it has to be a column vector. Absolutely right. Okay? Now, it says solve it. Okay? Now, what technique do we have for solving systems of equations so far? It's either Gauss-Jordan or Gauss elimination with back substitution. So basically we would have to do it like this. 1, negative 2, 1, 2, 3, negative 2, with a 0 and a 0 here. And we start our elimination, so what would we have first? Second, you got a 1 at the top, very good. You need a 0 below it. How do you make that happen? Negative 2 times row 1 plus row 2. Okay, we're using the top row, 1, negative 2, 1, 0, and what's the new second row? Say again? 0, okay, that's why we did it. Next. Is it? Be careful. Negative 2 times negative 2 is? Positive 4 plus 3 is 7. Next. Next. Negative 4. And next, I can do that one. Help me with 0. Good. Okay. Now, this is a little on the messy side, isn't it? What would be your next move? What's the next thing you want to happen? You want the 7 to be a 1, don't you? And how's the only way we can do that? Divide by 7. Okay? So this will be divided by 7. Actually, that's divided by 7 too. This is divided by 7, and that's divided by 7. So that new matrix then, and what it is row 3 divided by 7. Okay? That's what we did. So then we would have a 1, negative 2, 1, 0. What you tell me what the bottom row would be? 0, 1, negative 4 sevenths, one of my favorite numbers in the whole world, and 0. Okay. And I should have erased stuff at the beginning. I didn't realize this was going to be this big of a problem, I might say, this taking this much room. That's why it's not that big of a problem, but it just takes a lot of room. So I didn't need that anyway, so I should have erased it back when I could have fast, but I didn't. So let's get it done now. Okay. What do we want to happen next? Second? Okay. You could do that if you're going to do Gauss elimination. The book chose to do Gauss-Jordan elimination. I don't really care, but let's just do what the book did. So what we want to happen next? Sort of the practice of Gauss-Jordan. You want the negative 2 to become a 0, so what would we do to make that happen? You want that negative 2 to become a 0 right there. Second, 2 row 2 plus row 1 is the new row 1. Okay? So, since I'm using the second row, I'll leave it alone. I don't need that big a bracket, but 0, 1, negative 4 sevenths, which is a really ugly 4. Let's see if we can clean that up just a tad. Okay, that's better. Okay, 0, I can do that last one. And then what's your new top row? 1, 0, negative 1 seventh. Very good. And 0. Okay. Now, that is where the book now does the parameter. What parameter you want to use? I don't care. Give me one. Say again? W. Okay. And which one you want to be W? Let x3 equal W. Okay. So that produces x3 equals W. What would your x2 equal? Read that second row to me right now. That would be x2 minus 4/7 x3, which is w, is equal to 0. And what would that produce? x2 is equal to 4/7 w. Okay? And what does the top row tell you? Say that again a little louder. x1 is equal to 1/7 w. Okay? Now, if I were going to check that, okay, I think what I would choose, what w would you choose? You get to choose any w you want to. The easiest one I can think of is 0. Ah, yes, you got it. And if you put 0, then x1 would be 0, x2 would be 0, and 0, 0, 0 certainly makes that true, doesn't it? No matter what you got over here, if all your x's are zeros, then when you multiply them out, you're going to get 0 to 0. Okay. Yeah, that was a trivial solution. We knew that one worked because this was a homogeneous equation. Okay? But give me another w that's still pretty easy, but not maybe quite that easy. Let w be, okay, 1, okay, wouldn't be so awfully bad, but okay, we'll do 1. Okay, if w is 1, then x1 is 1/7, and x2 is 4/7, right? Second? I like 7 better, okay? So let w equal 7, that makes x1 equal 1, and x2 equal 4. Let's see if that works, okay? Here was our original equation. That would be 1 minus 8 plus 7. 0, right? And then this would be 2 plus 12, no, yeah, plus 12 minus 14. That's 0. Yes, that works too. So you have an infinite number. And for most of my w's, I think I would choose multiples of 7, like -7, 14, and minus 14. You know, they would make those a little bit easier to do. Infinite number of solutions. And you could use 1 and 2 and 17 and 14 and whatever.
So, basically, this is going to be like substituting 0 for like 7 or something.
Okay, no, what I did when you told me to use w equals 7, okay, if you do that, x1 would be equal 1, right? 1/7 times 7 is 1. x2 would equal 4. Because 7 times 4/7 would be 4. And x3, of course, you chose to be 7. So I plug those back into with these coefficients. Okay? In other words, I'm doing my matrix multiplication now. Only I'm
So
using,
you plug those in.
yeah,
There, okay.
yeah, that's it. Those I plug in here. That would be 1 minus 8 plus 7. Yeah, that adds a 0, right? And then using, in the second row, I would do 2 plus 12, 14 minus 13. Just plugging those three numbers.
Okay, so.
Yeah. And any other w you choose, 1, that would work too. And you have 1/7, 4/7, 1. Okay? Let's do that one. Emmanuel loves it so much. Okay, that would be 1/7 minus 8/7. That would be minus 1 plus 1. That would be 0. Okay, and the next one would work 2. That would be, I'm trying to think what it would be now. 2/7 plus 6/7. That would be plus 12/7. Be 14/7, which is 2, and then you would have negative 2 times 1. Yeah, that would be 0, 2. Yeah. So they work. Yeah. All right.
It's not.
Say again? Oh, no. How could it be? Okay. Let's just make sure the book got it right, too. They got x1 equal t, x2 equal, they'd use t, and then 4t and 7t. That's fine, too. We did it a different way. It works, okay? Now, here's another way you could have written your answer then. Let's use those 3 that we have there, and then we could multiply this by w, and that gives us our whole equation. X is equal to 147 multiplied by any w you happen to choose. Okay? Different w's give you different values. We'll start next time at the top of page 46, partition matrices.
So,
Yes.
if that's like was on the test, like what would be the answer?
The answer is basically either this one, 1/4 w, negative 4/7 w, or you could have done one. Oh, I left off my minus, didn't I? No, that's not a minus. It's the 4/7. That's right. They use t, any letter you put there, 147 or 17471. Either of those would work, times your parameter, t, w, whatever you choose. That's your answer. All right, so we'll be, let me give you some homework exercise. I knew you were waiting around for them. Okay, do either 1 or 3 or both. Do any of the odds 5 through 15. Okay, no, 5 through 11, sorry. Then do either 15 or 13 or 15 or both. Any of the odds 17 through 29. Any of the odds 31 to 37. Do 39. Do 41. I'm sorry, do any of the odds 41 to 47. I guess we'll stop there. We'll pick up the rest of those next time. Okay, good deal. Have a good weekend. Well, wait, I'll see you all again, right? Different classes, but I'll see you all again in the sweet by and by. Okay. All right. Why did it do that?